Hello, and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be doing Unit 8, Lesson number 4, the dot product of two vectors. So at this point, we've taken vectors and we've added them, and we've gotten vectors. We've multiplied them by scalars, and we've gotten vectors. We've subtracted them and gotten vectors. So it's logical to see if we could do other things with vectors that we do with normal numbers. Can we multiply them? Can we divide them? And the short answer, honestly, is no. Now, with vectors, though, there are two types of products. All right, there's what's known as the dot product and the cross product. Now, this really isn't multiplying two vectors. The word product is even, in a certain sense, a little bit weird. Now, normally, what I would like to do is develop the idea of a dot product. We're not going to work with the cross product in this course, but develop the idea of the dot product in order to solve some kind of a problem. With this particular topic, what I've decided to do is just to give its definition. So here we go. The dot product of two vectors, u and v, which is symbolized, no great surprise, by a little dot, okay, little dot, not an x, is simply defined as the magnitude of u times the magnitude of v times the cosine of the angle in between them, where that angle is between 0 and 180 inclusive. Okay, so that's just what the dot product is. The size of u times the size of v times the cosine of the angle in between. All right, now you have no reason right now to understand why it's used, how it's used, where it came from, or anything like that. All right, I'm just going to define this. Now, let's talk about the dot product a little bit. There are four observations I want to discuss. The first one, and this is extremely important, is that the dot product is a scalar. Now remember, when we added two vectors, we got a vector. When we multiplied a vector by a scalar, we got a vector. And yet here, the dot product is a scalar. And you can tell that by just looking at its definition, right? This thing is a scalar. This thing is a scalar. This is a scalar. So they're just normal numbers. A normal number times a normal number times a normal number is just a normal number. So the dot product of two vectors is not a vector. Now let's talk about its form. All right, I really want you to key in. The next three observations all depend on a single thing. So let's kind of talk about that before we get into observation 2. All right. If we really look at this form, then this is a positive number, and this is a positive number because they're lengths. Therefore, whether the dot product is positive, negative, or 0, all depends on the angle. All depends on the angle. And the only way the dot product can be 0, assuming that neither u nor v is the 0 vector, is if the angle is 90, right? Because the cosine of 90 degrees is equal to 0. This is really, really important, right? What it means is that if I do a dot product and I get 0, it means that the two vectors must be perpendicular to each other. Okay, so a dot product of 0 means that vectors are perpendicular to each other. But we can go a little bit further. Right, we can say, look, the only way that the dot product is going to be a positive number is if the angle between the vectors is between 0 and 90, right? Because the cosine of that angle will be positive in this interval. Likewise, we can also say that the only way that the dot product is negative is if the angle is between 90 and 180, because in this area, cosine of theta is less than 0. Remember, cosine is the x-coordinate on the unit circle, so it's negative here and it's positive here. All right, this is really kind of cool. Next lesson, all we're going to do is work on the geometry of the dot product, because it tells us quite a few things. But for right now, I want you to kind of sit back and really think about all that. Pause the video if you need to. All right, because we're going to scrub this out and we're going to start using it. Ready? Okay, let's take a look at exercise 1. It says a vector u has a magnitude of 12 and an angle of 126 degrees with respect to the positive x-axis. Draw it. Right? Just draw it. Now it's 126 degrees, so it's going to look something like this. Magnitude of u. Right? This is 126 degrees. Then I have vector v that has a magnitude of 8. So it's a magnitude of 8, and its angle is 24 degrees. And we want to find u dot v. Well, just by definition, u dot v is the magnitude of u times the magnitude of v, both of which we know, times the cosine of the angle that's in between them. Well, let's see. The magnitude of u is 12. The magnitude of v is 8. But what's the angle in between them? Pause the video for a moment to figure that out. All right. Easy enough, isn't it? Right, we know that that entire angle is 126 degrees. We know that that angle is 24 degrees, so the angle in between them, our theta, if you will, is 126 degrees minus 24, or 102 degrees. Right, so that's the angle in our calculation. We're not going to get a nice number here. We are going to get one that's negative, because the two vectors form an obtuse angle. Yeah, the dot product is negative 19.960. Now, let me be very clear. That number, negative 19.960, that shouldn't really mean anything to you. It does have a meaning, but it shouldn't mean anything to you right now. The only thing I really want you to get out of this is, number one, a little work with the formula, and number two, the fact that because those two vectors were obtuse with respect to each other, their dot product turned out to be negative. That's it. Now, this was a little bit tricky, wasn't terrible, right? But you can imagine how tricky it would be if the vectors were given in component form. Take a look at exercise 2. It says find the dot product of each pair of vectors using the shortcut method. Now, you don't know the shortcut method. It's really nice. It's super easy. I'll show it to you in a second. But think about how much harder this would be if we didn't have this shortcut method, which we don't have yet. You could still do it. You know, you could take vector u and you could kind of draw it out, and you'd say, oh, well, let's see, it's 3 this way and 4 this way, so here would be vector u, and then vector v would be, okay, it's 7 this way and 2 this way, so here would be vector v, right? And then we could figure out this angle, and we could figure out this angle, and therefore we could figure out the angle in between them, and then we could put a smiley face on and big ears, and now it kind of looks like me a little bit. Anyway, let's just get rid of that. That's just silliness. So, you know, we could do all of that, but it would be a pain. And then how in the world would we deal with it in the three-dimensional case? How would we even figure out the angle in between them? Ironically, by the end of this lesson, we'll be able to figure out that angle. But let me now teach you the shortcut method. Okay? Now, the shortcut method is weird, and I'm going to prove it to you in a moment, but here's all you do. You take the x component of this vector and the x component of this vector, and you multiply them. Plus the y component of this vector, make sure to include that negative, times the y coordinate of this vector, and that's a positive, and you simply add those two. So we get 21 plus negative 8, which gives me 13. And that's my dot product. That's it. Now, why that is equivalent to what we did in exercise 1, that's going to have to wait until exercise 3, where we will prove the shortcut method, at least for two-dimensional vectors. But it's really super simple. Right now, for three-dimensional vectors, if I want v dot a, right, I'll do negative 2 times positive 6. I'm going to write all of this out. I'm sure many of you would just do some of it in your head. Then positive 5 times positive 3. And then negative 1 times positive 7, right? That'll give me negative 12 plus 15 minus 7, and that would give me negative 4. Now, as an aside, right, and again, more on this tomorrow, but notice that in this particular problem, v dot a was less than 0. And that means that they must be obtuse with respect to each other. In other words, you know, if v is pointing this way, that's got to be an obtuse angle, versus letter A, right? That's got to be an acute angle because the dot product is positive. Okay? Shortcut method, really cool. Multiply all the components together and then add them. Simple. I'm going to clear it out, so copy down anything you need to. Here we go. And let's move on. Oh, proving the shortcut for 2D vectors. So why is it that if you have u, which equals ai plus bj, and v, which is ci plus dj, why can you just multiply a and c, b and d, and get the dot product? Now again, what I want you to realize is that, what we're saying is we're saying that u dot v by definition is the magnitude, oops, that's weird, is the magnitude of u times the magnitude of v times the cosine of the angle in between them. Okay, that's what we're saying. So somehow what we want to show is that this gives the same result as this, or really more appropriately, we're almost going to always use the shortcut, right? And what we want to do is make sure that the shortcut is equivalent to this. All right, so here we go. This is kind of a neat proof, but then again, I'm a geek. So here I've got vector u, all right, and I'm going to actually write it in this form, ab. All right, and then I have vector v, and I don't really know what it looks like, right? I'll kind of draw it like that. Remember, it's got components c comma d. Now I'm going to actually draw this vector in. Okay. Now notice that is not the vector u plus v. All right, but what vector is it? This is an important vector, but what vector is it? I'd like you to think about that for a moment, okay? Did you figure it out? The vector that I have the question mark for is actually the vector v minus the vector u. Just think about that. We've talked about this on the homework, so if you haven't been with me the entire time, you might be a bit confused about this. But clearly, if I add this vector to this vector, I must get this, right? And u plus v plus negative u should be v, right? So this has got to be v minus u. All right. Now, the beautiful thing is, because I've got u and v in component form, I can also say what this is. This is just c minus a and d minus b. Fair enough? And this is theta. Right? That's the angle in my dot product. So now, we can now say, using the law of cosines, we can now say that the length of v minus u squared must be the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times cosine theta. Right? We can say that. We can definitely say that. All right, but here's the cool thing. Keep your eye on the ball. This right here, this is u dot v by definition. I mean, take a look at it. Seriously. There it is, right? That's u dot v. All right, so good, because we needed to get u dot v involved. All right, we'll put that in a second, but let's think about this. How do we find the length of v minus u? Well, we would take its x component, and we'd square it, and we'd take its y component, and we'd square it, and then we'd take the square root, but then we'd square to get rid of it. Same thing with the magnitude of u, right? That would just be a squared plus b squared. The magnitude of v, c squared plus d squared, and then I'm just going to put minus 2 u dot v. Okay, because that's what this is. All right, let's just do some foiling, right? What is this going to be? That's going to be c squared minus 2ac plus a squared. This is going to be d squared minus 2bd plus b squared equals a squared plus b squared plus c squared plus d squared minus 2u dot v. Don't lose sight of what we're trying to prove. We're trying to prove that u dot v is a times c plus b times d. Well, let's see. You know what? There's a c squared on this side and there's a c squared on this side. Oh, hey, look, a b squared and a b squared. Oh, what do you know? An a squared and an a squared. My goodness, it's a d squared and a d squared. So I get 2 times ac minus 2 times bd is equal to negative 2 u dot v. Oh, now I can divide both sides by negative 2, and I find that u dot v is equal to ac plus bd, and that is QED. By the way, if you were ever wondering, QED is a phrase that you'll oftentimes see professors put at the end of a proof or a derivation. It stands for quod erat demonstratum. It's something that Euclid put at the end of almost all of his proofs, and what it really means is that which was to be demonstrated. In other words, I promised you I was going to show you that u dot v was a times c plus b times d, and I delivered, or at least I hope I did. Anyway, I'm going to clear out the text, and then we'll move on. Okay, here we go. It's gone. All right. Now let's use the dot product a little bit. And this is so cool because now we have 2 ways of finding the dot product. Well, not 2 ways of finding it, but 2 ways to think about it, right? One way is this idea that, u dot v will be, the magnitude of u, the magnitude of v times cosine theta. The other one is that u dot v will be, if you will, the product of the x components, the product of the y components added. So this particular problem is a very important one because it's a classic with the dot product. I will guarantee to ask my students this on every test involving the dot product. I've got these 2 vectors, u. I'm not even going to attempt to draw them realistically, v. And I want to figure out the angle in between them. All right? Well, think about this. We can certainly find u dot v just using the shortcut method. Let's do that. That would be 6 times negative 1, right, plus 2 times 8, and that's going to be negative 6, 10. Right. Now come over to this formula. So we know what u dot v is. It's 10. We can figure out the magnitude of u. We can figure out the magnitude of v. Let's do that. The magnitude of u will be the square root of what? 36 plus 4. Root 40. Don't even think about simplifying that radical unless it's a perfect square. Radical v will be the square root of 1 plus 64, or root 65. So look what we have. We can now take this formula and say, well, u dot v is 10. The magnitude of u is root 40. The magnitude of v is root 65. And the only thing I'll have left is cosine theta. So in fact, cosine theta is going to be 10 divided by root 40, root 65. Then I can just do the inverse cosine. Cosine's beautiful because it's not ambiguous. It's unambiguous, meaning that all I have to do is do the inverse cosine of that. I don't have to worry about anything else. I'm not going to write all that mess down again, but that would go in here. As long as I've got my calculator running and I'm good to go, I will be at 78.690. Cool. Make sure you can do that if you're one of my students. In other words, if I give you 2 vectors in component form, make sure you can find the angle in between them. It's really nice. It's very algorithmic. You use the shortcut process to figure out what u dot v is. You figure out the magnitude of u, the magnitude of v, and then the only thing left to figure out is the angle. Very important problem. Pause the video now if you need to. All right, I'm going to clear out the text. Okay, last problem. Here we're going to deal with some real-life vectors. We've got a velocity vector and an acceleration vector. You already know in one-dimensional motion that acceleration is the derivative of velocity. We still haven't really gotten into that too deeply in multi-dimensional motion, but we will soon. It says, find the angle that separates the velocity and acceleration vectors if placed tail to tail. Why does this angle matter? What do you think it implies about the speed? So what I'd like you to do now is take a look at what we did in exercise 4, pause the video, find that angle, and think about the other two questions. All right, let's go through it. Very, very mechanical, right? So V dot A is going to be the magnitude of V, and my arrow symbols are getting terrible. The magnitude of A times the cosine of the angle in between. All right, we'll figure out V dot A using the shortcut. I always kind of do this at the side. What do I have? Negative 5 times 2 is negative 10. 2 times negative 1 is negative 2. Negative 1 times negative 3 is positive 3. So that'll give me V dot A is negative 9. I'll work out the magnitude of V over here. That will be the square root of 25 plus 4 plus 9. Looks like another ugly radical, root 38. We'll figure out the size of A. Same song, second verse. What do I have? 4 plus 1 plus 1. Square root of 6. I have everything, right? Come back over here. Negative 9 is the square root of 38 times the square root of 6 times cosine theta. Cos theta equals negative 9 divided by root 38, root 6. Do the inverse cosine, and theta will be 126.587 degrees. All right, so there's the angle that separates them. Now think about that. What that means is that if I drew the two vectors, forget about their lengths, just sort of drew them. And what that would say is that they're kind of like this, 126.587. Now the reason that that angle matters is that the acceleration is what's forcing the velocity to change. Now in multidimensional motion, the acceleration not only changes the length of the velocity, but it also changes the direction that the velocity points in. So that's maybe why the angle matters. But what does it imply about the speed? And this is really cool. It implies that the speed is decreasing. Now think about this. In one-dimensional motion, right? In one-dimensional motion, we learned that speed would decrease when acceleration and velocity had different signs, and speed would increase when they had the same sign. And that really was all about whether acceleration and velocity pointed in the same direction or pointed in opposite directions. Now it's not so easy because there's more than just same versus opposite. Now there's sort of like, same, completely the same, completely opposite, perpendicular, or somewhere in between. These two vectors are more opposite of each other than they are the same with each other. So what that means is that speed's going to decrease. We're going to look at that more later on when we get into multidimensional motion, but it is kind of one very quick application of the dot product. I'm going to clear out the text, so please copy down anything you need to, pause the video. Okay, here we go. All right, well, so now we've seen quite a bit about vectors, their notation, the way to manipulate them, a crazy thing called the dot product, which will allow us to even figure out how those vectors are oriented in space, whether they're two-dimensional or three-dimensional doesn't really matter. Next time, we're going to concentrate exclusively on the dot product and its geometry and what it tells us about the relative orientation of vectors. All right, but for now, let me remind you that this has been an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.